Morning. Welcome to lecture number 15. Today we are going to discuss volume stability, okay, shrinkage and creep. We mentioned about shrinkage and creep a little bit in previous lectures. Today we're going to discuss these two in details. Right. So what are the reasons cause volumetric change of concrete? There's many reasons for that. For example, temperature change. Increased temperature, the concrete will expand. Reduced temperature, the concrete will shrink. Okay, or mechanical loading. Okay, we apply a load over the time. The dimension of the concrete will change. Okay. We call that creep or relaxation. Okay, or moisture change. We talked about dry shrinkage before. Dry shrinkage is shrinkage because we have moisture loss. Okay, either the moisture loss to the environment or the moisture loss due to hydration. In that case, we call that self-desiccation. Hydration of cement will also cause another type of shrinkage called chemical shrinkage. Some harmful chemical reactions such as carbonation, which is carbon dioxide coming from the air, will react with alkalis, such as calcium hydroxide in concrete. We call that carbonation. Or sulfide attack. We talked about sulfide attack before, and also ASR, or alkali silica reaction. Okay. All these chemical reactions will cause either expansion, sometimes shrinkage of concrete. Okay. So let's first of all look at volumetric change due to loss of water. Okay, there's several different types of shrinkage due to loss of water. Okay, plastic shrinkage is loss of water to the air when the concrete is still in fresh state, so before set time. Dry shrinkage means loss of water to the air in hardened concrete after concrete set. Okay. Chemical shrinkage is reduction in the total volume of solid and also liquid during the hydration process. Okay. Autogeneous shrinkage. This is caused by so-called self-desiccation. Only occurs in concrete with very low water to cement ratio. Okay. Self-desiccation is also called dry internally due to hydration. Carbonation is hydrated cement paste react with CO2. Okay, meaning CO2 react with calcium hydroxide. Okay, so we'll talk about this 1, 2, 3, 4, 5 different types of shrinkage in more details. Let's look at plastic shrinkage first. Okay, again, it occurs while the concrete is still in the plastic state before initial set time. Okay, for normal concrete, the initial set time is around 2 to 3 hours. Okay, so very early stage. During that time, surface of the concrete is still stiff, but becomes stiff, but it's not very strong. Okay, when we have high temperature or low relative humidity in the air, or we have high wind speed, that will accelerate water evaporation. Okay, sometimes water can be sucked by surrounding structures. Okay, that may also cause plastic shrinkage of fresh concrete. The size of crack is around 0.3 to 1 meter in space. The depth of the crack is around 1 to 2 inches. Okay, how we can reduce plastic shrinkage? Because plastic shrinkage occurs by evaporation or suction of water to the surrounding structures. So we can, first of all, moisten the surrounding structures. Okay. Sometimes we can also increase amount of aggregate, okay, because cement paste will shrink more than mortar, and mortar will shrink more than concrete. That is because shrinkage only occurs in cement paste. Aggregate will never shrink. So the more aggregate in the system, less shrinkage. Okay. We can also use wind bricks, sunshade to reduce the wind, reduce the temperature, or using fogging to provide extra moisture, plastic covering. Okay. Or we can using cooling wetting of aggregate. Okay, we pre-soak aggregate in water, and after we cast the concrete, this aggregate will slowly release moisture to cement paste, so reduce plastic shrinkage. We can also use fibers. Fibers cannot prevent concrete from shrinkage, cracking, but it can reduce the size of shrinkage, a crack, due to shrinkage. Okay. For example, here shows how the percentage, the volume percentage of fibers, okay, affecting the size of the crack. As we can see, increased percentage of fibers, we can reduce the size of crack. Okay. The second type of shrinkage is called drain shrinkage, and we mentioned about this many times before. This is due to loss of water to the atmosphere in hardened concrete. Okay, after concrete set, water is lost to the air. It occurs when the pore water in the pores in concrete diffuse to the surface. The risk of drain shrinkage will increase as porosity goes up, because the higher porosity, the higher diffusivity. So the water will be easier to evaporate. The curve here shows us how the drain shrinkage will increase over time. Okay, the drain shrinkage will increase over time. If we re-wet the concrete, some of the shrinkage is reversible, as you can see from here. Okay, but some of the shrinkage is irreversible. The reason for this irreversible shrinkage is because when shrinkage happens, we have some permanent deformation due to slippage of CSH sheets. Okay. As we can see here, this is old slides from lecture number 4. Okay, here shows waters in hydrated cement paste, and we have interlayer water, which is water between the CSH sheets. Okay. Interlayer water will lose below 11% RH. Okay. Capillary water, which could be in large voids or smaller voids. Okay, the water in larger pores, other than 50 nanometer, we call that free water. The reason for that is because when free water loss in larger pores, not too much shrinkage will occur. When water loss in smaller pores, between 5 to 50 nanometer, that will increase shrinkage because the size of the pores will control how much shrinkage stress. We call that capillary retention. The smaller the pores, when water evaporates from these smaller pores, the shrinkage stress will be higher. Okay, we'll talk about that in more details in a moment. Adsorbed water is the water on the surface of solid. Okay, only around 6 layers. Okay, and finally we have chemically combined water, which is the water in CSH. Okay, chemically combined water is very hard to lose, only under very high temperature. Look at this curve of dry shrinkage. This is very interesting. So here shows how much shrinkage occurs versus the weight loss. As we can see, the slope of this curve are quite different. And this is due to loss of water at different type of water. Region 1 is water loss from larger capillary pores. It occurs between 100% to around 90% RH in the pores. Okay, so that is region 1. For region 2 is water loss from smaller capillary pores. Okay, what we can see comparing region 1 and region 2 is the slope in region 2 is much steeper, which means for the same amount of reduction in RH, region 2 will have more shrinkage. The reason again is because in region 2 is water loss from smaller capillary pores. When we reduce the pore size, the shrinkage stress will be higher. So for the same amount of reduction in RH, region 2 will have more shrinkage. Region 3 is loss of water of adsorptive water. Okay, between 55% RH to 10% RH. Okay, the slope is pretty small. And region 4 is loss of interlayer water or the gel water from CSH. Okay, again, all right. So loss of water, different type of water will cause shrinkage in different regions. Okay, and region 5, only occurs when we increase the temperature of concrete to very high, okay, about 105 degrees. Okay, but the shrinkage value is very high, as we can see here. The slope of the curve is very steep. Okay, but most commonly, dry shrinkage occurs in region 1, region 2, sometimes region 3 and the region 4. Okay. Here shows shrinkage for different specimen. The water cement ratio is the same. The volume of algae is also the same. The only difference for this specimen is S to V, which is the ratio of surface of the specimen to the volume of specimen. Okay, remember dry shrinkage is caused by evaporation of water to the air. So the more surface, the easier for concrete to dry shrinkage. Okay, so as we can see here, the higher the surface to volume ratio, the faster the dry shrinkage. However, the final value of dry shrinkage is the same. Okay, it does make sense. The more surface to volume ratio, dry shrinkage occurs faster, but the total dry shrinkage does not change. Okay. All right, so that is dry shrinkage. Next one, let's look at chemical shrinkage. All right, so what is chemical shrinkage? By definition, chemical shrinkage is reduction in the absolute volume of solid plus liquid during the hydration process. Okay, for example, the chemical reaction between C3S plus water, we have calcium hydroxide plus CSH. Okay, the total volume of calcium hydroxide plus CSH will be less than the volume of C3S plus water. Okay, we call that chemical shrinkage. Okay, as we can see from here, initially we have 60% of water plus 40% of unhydrated cement. Okay, after 50% of degree of hydration, we have some unhydrated cement left. we have some water left, and then we have hydration product, and we have some gel water, and we have some oils. Okay, so the total solid plus liquid right now is only 96.3% compared to 100% at the beginning. Okay, and we call that chemical shrinkage. At 100% hydration degree, we have around 7 to 10% reduction in total volume. And chemical shrinkage is the reason we have capillary pores inside concrete. All right. So after we introduce chemical shrinkage, let's look at autogeneous shrinkage. Autogeneous shrinkage caused by self-desiccation in concrete with very low water to cement ratio. Okay. Self-desiccation is also called internal drying due to hydration. Okay. Let's look at this. Okay, let's say we have unhydrated cement mixed with water. Okay, and we wrap this cement paste with aluminum sheets. Okay, that will ensure water will not evaporate to the air. Okay, that there is no plastic shrinkage, there's no dry shrinkage. Okay, but chemical shrinkage will happen. Okay, and we know due to chemical shrinkage, the total solid volume plus liquid volume will be lower. Okay, so let's say at initial set time, we have a little bit chemical shrinkage. And after initial set, chemical shrinkage will continue. That will generate pores, okay? These little pores will generate it inside hardened cement paste. Okay. However, after initial set, the cement paste form a solid, have some strength, and this cement paste will try to resist this further deformation, more chemical shrinkage. So that will force, this will cause the formation of voids inside the microstructures. Okay, so look at here. After initial final set time, we have some autogeneous shrinkage. Okay, this is before the set time, which is equal to the chemical shrinkage. After set, because concrete will continue to have chemical shrinkage, and the pores will dry out, so we have some autogeneous shrinkage after set. If we count the total volume of these pores together, okay, this is cumulative voids. Again, this is the volume of these small pores added together. Okay. And this part is called autogeneous shrinkage because this is reduction in the total external volume due to chemical shrinkage. Okay. And autogeneous shrinkage plus this cumulative voids is equal to the total chemical shrinkage, okay, which is absolute volume reduction. Right. So chemical shrinkage is the reason for dry shrinkage and also autogeneous shrinkage, because without chemical shrinkage, we will not have these capillary pores inside cement paste. This figure shows us autogeneous shrinkage for two types of water concrete. One is water cement ratio 0.05. Another one is water cement ratio of 0.3. Okay. For high water cement ratio concrete, there's not too much autogeneous shrinkage. Okay, as we can see from here, almost zero. But low water cement ratio concrete has a lot of autogeneous shrinkage. And the figure on the right shows us the total shrinkage. Okay. Total shrinkage including dry shrinkage, which is shrinkage due to drying to the air, plus autogeneous shrinkage, which is drying due to self-desiccation or drying due to hydration, and plus some of the thermal shrinkage. This is shrinkage due to temperature change. Okay. Right. Let's have a closer look at autogeneous shrinkage. Okay. Autogeneous shrinkage only occurs in very dense concrete, which has very low decimal ratio, sometimes has some of silica film inside it. Okay. Autogeneous shrinkage only occurs in concrete with low water decimal ratio, water decimal ratio below 0.0442. Okay. The mechanism of autogeneous shrinkage is actually the same as dry shrinkage. That is drying of the capillary pores. But dry shrinkage dry the pores when the water go to the air. Autogeneous shrinkage dry the pores due to self-desiccation or hydration of cement compound. Because autogeneous shrinkage only occurs in low water cement ratio concrete. So to limit the amount of autogeneous shrinkage, we need to place a lower limit on water to cement ratio. And because for concrete with low water cement ratio, microstructure is very dense. Okay, traditional curing is not very effective because even if we provide actual curing from outside, and because the concrete is so dense, this water from outside may not penetrate deep enough and release the drain of the pores. Okay, so that's the problem for some of the high strength concrete. Okay, some high strength concrete will crack due to autogeneous shrinkage, and traditional curing is not very effective. So let's further look at autogeneous shrinkage and see why it only occurs in low water cement ratio concrete. Here shows a concrete with water cement ratio of 0.5. Okay. After initial set, we have skeleton form. Okay. And we have more drain shrinkage. Okay. And we have porosity. And the pores in this high water cement ratio concrete is still saturated because we have actual water in these pores. Even all the cement is fully reactive. So the pores is not dry. On the other hand, for low water cement ratio concrete, due to chemical shrinkage, the pore will be dried off because we have more cement than water. Okay, so all the water will be consumed due to hydration, a chemical reaction between cement paste, between cement and water. So the pores will dry due to self-desiccation. And drying of these pores will cause autogeneous shrinkage. And that's the reason why autogeneous shrinkage only occurs in low water cement ratio concrete. All right. So the mechanism of shrinkage, both dry shrinkage and autogeneous shrinkage is caused by capillary surface tension. Okay. When water leaves the pore system, we have the curved menisci, okay, which is the surface of pore water. Okay. The curvature decides how much shrinkage stress it will generate. The higher the curvature, the higher the shrinkage stress. Okay. And this phenomenon is caused by many factors. Okay, as we can see from here. Right. The surface tension of the pore solution, the temperature of the concrete, the size of capillary pores. Okay, these three factors will govern the radius of menisci curvature. Okay, it will cause mechanism equilibrium. We'll talk about what is P double prime, what is P prime. Okay. Some other factors will affect pore size, concentration of the salts. Okay, this will cause physical chemical equilibrium. Okay, we have 2 gamma over alpha, also relative humidity in the pores, temperature. This is another parameters. Okay, combining all these factors together, we have the famous Kelvin-Laplace equation. And here is definition of these parameters. P double prime is called vapor pressure, and P prime is called pore fluid pressure. The difference between these two pressure is shrinkage stress. Okay, gamma here is surface tension of the pore solution. R here is pore radius. Okay. RH is internal relative humidity. R is a constant, universal gas constant. And T is temperature in kelvins. And V prime is molar volume of water. Okay. Some of these parameters does not change as much, such as R and temperature. But some of them will change, such as pore radius, surface tension, sometimes will also change. Okay. So based on this equation, we know if we reduce the pore size, R here, will increase the shrinkage stress, which is difference between P double prime minus P prime. If we increase the surface tension, gamma will also increase the shrinkage stress. Okay. If we reduce RH, relative humidity, will also increase shrinkage stress because this is minus natural log. Okay. So RH, surface tension, and gamma are the 3 dominant parameters controlling shrinkage stress. So other things such as temperature, R, and V prime does not change as much typically. Okay. Let's go back to the previous slides. One of the chemical admixtures is called shrinkage reducing admixtures, or SRA. So these admixtures can reduce the surface tension in the pore solution. So as a result, the surface tension, which is gamma here, reduced. So we can reduce the shrinkage stress. As a result, shrinkage will be reduced. Okay. So Kelvin-Laplace equation allows us to correlate relative humidity, the pore size, and also surface tension of pore solution into dry shrinkage stress. So sometimes we can even quantify how much shrinkage certain concrete will experience. All right, go back to these slides. We showed these slides before, moments ago, and we know region 2 has steeper shrinkage, which means for same amount of reduction in RH, region 2 has more shrinkage. The reason for that is because in region 2 is drying off smaller pore size, smaller pores. Okay, and because due to Kelvin-Laplace equation, reduce the pore size, reduce R, will increase the shrinkage stress. So the shrinkage will be higher. All right, so what affects shrinkage of concrete? Mixed proportion. Okay. If we increase water cement ratio, dry shrinkage will increase. Okay, because we have more water in the system, so more water can evaporate. Also because the pores in concrete with larger water cement ratio is larger, so the drying is easier. Okay, but increased water cement ratio will reduce autogeneous shrinkage. Remember, autogeneous shrinkage only occurs in concrete with low water cement ratio. Okay, it is caused by self-desiccation. Right. Remember, only cement paste will shrink. So if you increase the volume of aggregate, shrinkage, including dry shrinkage and autogeneous shrinkage, will be reduced. Okay. If we increase the stiffness of aggregate, remember, aggregate will not shrink. So higher stiffness of aggregate will try to restrain the shrinkage of cement paste. So the shrinkage will be smaller. The bond strength between the cement paste and aggregate is also important. Stronger the bond, the restraining effect of aggregate will be higher, so the shrinkage will be lower. Environmental conditions. Okay, relative humidity of the air, temperature, the wind speed, this will affect dry shrinkage, but not so much on autogeneous shrinkage. Okay, age of curing before drying. Increased age of curing, the concrete becomes stronger. Okay, and also dries later, so the shrinkage will be smaller. The ratio of volume of concrete to the surface, so increase the volume to surface ratio, the shrinkage rate will be lower, but ultimate shrinkage value will be the same. That is for dry shrinkage. Okay, so shrinkage describes a volumetric change caused by water loss, or due to desiccation, or changing temperature. Okay, when the concrete can shrink freely, typically it will not crack. Okay, cracking concrete happens when the concrete is restrained. Okay, so restraint will prohibit the length change. As a result, tensile stress will develop inside the concrete. When the tensile stress is higher than the tensile strength, concrete will crack. Okay. Right. Here shows a test called ring test, which simulates restraint shrinkage. Okay, so we can cast the concrete in the ring, okay, and we can measure the shrinkage stress and when the concrete will crack. It simulates the infinite strip because this is the ring. The concrete will be restrained by itself. Okay. We could also do the slab test. Okay, we can restrain the concrete from the two ends only. It's called restraint end, also called uniaxial tension. Sometimes we can also restrain the concrete from the two ends and also the bottom. Okay, so we can measure the size of the crack, when the crack will occur, and also the spacing between the cracks. Okay. All right. Sometimes the drying is not homogeneous in the concrete. So, for example, we have a concrete slab on grade. Okay. The dry shrinkage will be more for concrete closer to the air. Concrete closer to the ground will dry less. Okay, because anyway, dry shrinkage is due to drying of the concrete to the air. Okay, so we have moisture gradient. Closer to the air, we have more drying. Okay, closer to the ground, we have less drying concrete. And this moisture gradient will cause shrinkage strain gradient. So as a result, the concrete may curve like this because the concrete in the top layer will shrink more because it dries more. Okay, and this may cause the concrete to shrink, to curve, and also crack sometimes. All right, so that is shrinkage. Next, let's look at creep and also relaxation. Okay, what is creep? If we compress, apply a certain load on a concrete specimen, and we keep the load for a long time, the stress level will not change. Okay, but the strain will slowly increase over time. Okay, and we call this phenomenal creep. Relaxation means we keep the strain constant. We keep the delta L constant. Okay, and if we measure the internal stress of the specimen, the stress level will goes down over time. Okay, so why concrete will have creep and relaxation? Okay, actually is caused by similar reason as in the dry shrinkage. Okay, when we have stress in the concrete, sometimes this stress will cause slippage of between the CSH sheets, and some of this slippage is permanent, and some of this can be recovered. Okay. Creep occurs at room temperature or any other temperature, and creep for creep to occurs, it will under some type of load. Okay, without load, the concrete will not creep. Okay. And creep can result in long-term detonation. Sometimes can be up to 3 times of the instantaneous detonation. Okay. It may also cause loss of pre-stress in pre-stress concrete. Okay. And cracking can lead to more deterioration. Okay, increase the size of crack. And too much deflection could occur, could cause some serviceability problems. Sometimes creep relaxation can also be beneficial because it can reduce internal stress. Okay. For example, we have the beam and the load, and over the time, deflection will be much higher. Okay. For pre-stressed concrete is we apply pre-tension in the reinforcement. So the concrete will under pre-compression. Okay. Because concrete will creep, the tension stress in the rebar will be smaller over time. And we cause that stress loss in pre-stressed concrete. Okay. And creep will also cause stress redistribution. This is reinforced concrete beam. Okay, this is rebar. This is concrete. And because concrete will creep under the load, so concrete will become smaller. Steel will not creep as much. If the bonding between the rebar and the concrete is well enough, it will cause stress relief in concrete, which means steel will take more load and the concrete will take less load. Okay. And creep is caused by slippage between adjacent CSH sheets. Okay, this black lines is the CH sheets. And this slippage will increase when we have more absorbed water between the CSH particles. Less water, we have less shrinkage. This is similar to drain shrinkage. More water, we have more drain shrinkage. Less water, we have less drain shrinkage. And if you see the parameters cause drain shrinkage to increase, we also cause creep to increase. And same parameter cause drain shrinkage to decrease, we also cause creep to decrease. Okay, this is because the reason for creep and drain shrinkage is very much similar, a slippage of CSH sheets. All right, for example, external factors are affecting creep. If we increase the degree of hydration, we'll reduce creep. Same thing for drain shrinkage. Increased degree of hydration will also reduce drain shrinkage. Increased humidity will reduce creep. We also reduce drain shrinkage. Increased wind speed will increase creep. We also increase drain shrinkage. Increased cooling temperature will increase creep and drain shrinkage. Okay. And creep is also a time-dependent properties, depending on the load size and also depending on the load duration, because it's caused by slippage of CSH particles. Geometry, okay. So increase volume to surface ratio, that will reduce creep. It will also reduce drain shrinkage. Let's look at internal factors. Okay. So higher water cement ratio will increase creep. It will also increase drain shrinkage. Okay. Increased moisture or water content will increase creep, also increase drain shrinkage. Okay. Chemical admixtures, some water reducing admixtures and retarder may increase creep. Okay. For aggregate, more aggregate volume, it will reduce creep. Okay. It will also reduce drain shrinkage. Creep is also paste phenomenon, which means aggregate will not creep. So only cement paste will creep. So we increase volume of aggregate, creep will be reduced. Same thing for drain shrinkage. Drain shrinkage is also a paste phenomenon. Aggregate will not shrink. If we increase the stiffness of aggregate, the restraining effect of aggregate will be higher, creep will be lower, drain shrinkage will also be lower. More microcrack in concrete will increase creep, will also increase drain shrinkage. Increased amount of cement will increase creep and also drain shrinkage. Again, creep and shrinkage is paste phenomenon. Only cement paste will shrink and creep. Okay. Right. And here shows influence of loading on creep. Right. As we can see here, different level of loading, 99% of peak load, 80%, 60, 40% of peak load, and the back cell is the axial strain. So increase the percentage of peak load, concrete will have more creep. Okay, we have more internal stress, so creep will be higher. So that makes sense. The figure on the right shows us influence of age at loading, which means here at day 1, we apply the load. Okay, at day 3, day 7, or day 14. Okay, later age we apply the load, the creep will be less. That is because later age concrete become stronger, so the creep will be smaller. And here shows how we can simulate the creep of concrete. Okay, and we know concrete is viscoelastic materials. Okay, for elastic behavior, we can use spring to simulate. Okay, the stress is equal to E value times absolute, which is the strain. For the viscous component, viscous phenomenon, we can use a dash point. Okay, the strain is equal to the stress level over the viscosity. Okay. Here shows the Maxwell model, which is also called the series model. So elastic component is in series as the viscous component. So in this model, the stress level in the elastic component will be the same as the stress in the viscous component. Okay, and the strain will be addition. Okay, the total strain will be the strain from the elastic component plus the strain from the viscous component. Okay. And in current model, the elastic component is in parallel as the viscous component, which means the strain of elastic component will be the same as the strain for viscous component. And the stress level, the total stress will be the stress in the elastic component plus the stress in the viscous component. Okay, this is called Kelvin or parallel model. And sometimes we can combine the Kelvin and the Maxwell model together. Okay, some part is in parallel and some part is in series. Okay, just show you some modeling work we can use to simulate the viscoelastic performance of concrete. All right. So today we discuss shrinkage and creep. Okay. Basically, the viscous component of concrete. The volume or the length of concrete will change over time. Okay. We discuss different type of shrinkage, from plastic shrinkage to dry shrinkage to chemical shrinkage to autogeneous shrinkage. Okay. You should know the definition of this shrinkage. The governing mechanism of this shrinkage, the Kelvin-Laplace equation, and the difference between this shrinkage. How to reduce shrinkage? Okay, and what is creep and relaxation? And what are the affecting factors on creep and relaxation of concrete? Okay. And this is the reading suggestions. All right.